Welcome to this explainer. Look, we constantly hear about the booming energy transition, right? Millions of solar panels going up, massive wind turbines being installed, ambitious net zero goals absolutely dominating the headlines. But there is a huge, often completely invisible bottleneck standing in the way of actually delivering that clean power to the homes, the data centers, and the factories that desperately need it. So you got to ask yourself this central paradox. Why is record renewable generation not enough? Why isn't building all this incredible new clean energy hardware instantly solving our power needs? If you assume that rapidly expanding wind and solar means the transition will just magically show up in national power indicators tomorrow, you definitely wouldn't be alone. But the reality on the ground is, well, a whole lot more complicated. The answer really lies in a staggering backlog. Get this. Right now, there are 2,600 gigawatts of power projects waiting in the interconnection queue just to be connected to the grid. To put that into perspective, our entire current U.S. generation capacity is only about 1,300 gigawatts. So the backlog of projects just sitting there waiting to connect is exactly double the size of the entire existing U.S. grid. Okay, let's dive into this. We're going to systematically break down this massive problem and look at some actionable solutions. Our agenda today covers the renewable energy illusion, the interconnection traffic jam, common grid misconceptions, expanding the physical grid, maximizing existing capacity, and then we'll wrap it all up with a 5-point action checklist. All right, Section 1, the renewable energy illusion. You see, generation is just the first piece of the puzzle. Building those solar panels and turbines is literally just step one of the energy transition. The grid itself isn't some neutral pipe. It's an incredibly complex engineering system with hard thermal limits, strict voltage constraints, and serious stability requirements. And man, this is all happening during an era of completely unprecedented high-load growth. This surge is being driven by artificial intelligence, massive data centers, and the reshoring of manufacturing. Just to give you an idea of the scale here, AI queries consume 10 times the power of traditional internet searches. These high-load customers require massive blocks of firm 24/7 power, sometimes up to a full gigawatt per facility. This compounding need for computing power is just staggering, and it's putting immense, totally unexpected stress on central utilities that are already struggling to decarbonize. Moving on to Section 2, the interconnection traffic jam. It really helps to think of the power grid like a national highway system. Adding millions of new power generation sources without physically expanding the transmission grid, that's exactly like dumping millions of new cars onto a 2-lane country road. It just causes a massive system-wide traffic jam. The data paints a pretty agonizing picture of this. The median time from when a project developer submits that initial request to when the project actually achieves commercial operation, it's nearing 5 years now. 5 years! And a lot of them are running much, much longer than that. And what's truly mind-blowing is the sheer volume of projects that simply drop out because of these delays. Data from Eniverse shows that roughly 90% of renewable generation projects never even progress beyond the interconnection queue. And it varies wildly depending on where you are. In California's CISO market, you're looking at nearly an 8-year wait. In ISO New England, the wait times are shorter at 3.6 years, but late-stage suspension rates are incredibly high, anywhere between 46 and 79%. So only a tiny fraction of what's planned actually reaches operation. Okay, Section 3, common grid misconceptions. Because the grid is so highly complex, it's really easy to look at energy data and draw totally the wrong conclusions. We often confuse fast build-outs with usable power. To truly grasp the problem here, we absolutely have to separate nameplate capacity from delivered energy. Nameplate capacity is basically just a stock metric. It's the maximum potential generation of a wind or solar farm if conditions are 100% perfect. But delivered energy? That's the actual usable power making its way to homes and businesses. Thanks to grid constraints and congestion, that usable energy is often drastically reduced through what's called curtailment. So a country can look like it's light years ahead in capacity additions, but be way behind in actual delivered clean energy. Which brings us to Section 4, expanding the physical grid. Since we know generation isn't the whole story, the first major solution is to physically expand our network infrastructure to connect these remote, new clean energy hubs directly to the distant load centers. Now, if we're going to build new lines over super long distances, we've got to use the right technology. High voltage direct current, or HVDC, is technically far superior to traditional high voltage alternating current, HVAC, for long hauls. HVDC gives you much lower energy losses over those distances, it can connect asynchronous grids without messing up the frequency, and it requires much narrower right-of-way corridors. It is uniquely suited, actually absolutely critical, for bringing remote offshore wind power straight to coastal cities. But here's a massive reality check on the physical build-out crisis we're facing right now. Back in 2013, the U.S. completed nearly 4,000 miles of new high-voltage lines. In 2024, only 416 miles were built. So despite surging electricity demand and all these massive planned investments, our physical construction pace has basically plummeted. A huge reason for this drop-off? Supply chain bottlenecks. Severe global transformer shortages have totally wrecked timelines, doubling utility procurement lead times to over 120 weeks recently. Transformers are the absolute lifeblood of HVDC projects because you have to step up the voltage for transmission and then step it back down so we can safely consume it. Demand for HVDC lines is outstripping supply by 2.5 times right now. Simply put, if you can't get transformers, you can't expand the grid. So what do we do in the meantime? Section 5, maximizing existing capacity. Building new physical lines takes years, permitting takes even longer, and supply chains are super strained. We have to figure out what we can do right this second to bypass these physical delays. Enter grid-enhancing technologies, GETs, and distributed energy resources, or DERs. Think of these as software and hardware upgrades for the infrastructure we already have. Dynamic line ratings use real-time weather data so we can safely push more power through existing lines. Advanced power flow control shunts power from overloaded lines onto underutilized ones. Topology optimization software quickly sniffs out better grid configurations. And meanwhile, distributed energy resources, like on-site solar and battery storage, let high-load customers just bypass the centralized grid bottlenecks completely by generating their own local power. And the really crucial point here is that these aren't just pie-in-the-sky theoretical concepts. Take Great River Energy up in Minnesota. They installed just 52 dynamic line rating sensors across 10 of their transmission lines. By using this tech to monitor the actual real-time line conditions, they increased their mean line capacity by nearly 49%. I mean, that is a massive amount of unlocked power on wires that were already there, achieved at a fraction of the cost and time of building a brand new transmission line. On the regulatory side, we've also got FERC Order 2023. This is a game-changing policy reform that finally shifts the interconnection queue from a first-come, first-served model to a much smarter, first-ready, first-served cluster-based approach. It kicks out all the speculative queue-clogging projects by forcing developers to actually prove they have site control and financial readiness before they can even get in line. Plus, it financially penalizes transmission providers if they miss study deadlines, which creates some much-needed accountability on both sides of the equation. All right, Section 6, our 5-point action checklist. Let's pull all these incredible solutions together into a clear, actionable roadmap for unblocking the energy transition. If we seriously want to solve this, here are the steps we need to take. 1. Shift to HVDC lines for long-haul transmission and offshore wind to absolutely maximize efficiency. 2. Rapidly deploy grid-enhancing technologies, like those smart sensors, to squeeze every last drop of capacity out of the grids we have today. 3. Encourage the use of DERs for local high-load bypassing, so data centers and manufacturers can control their own power. 4. Strictly enforce those FERC Order 2023 readiness standards to clear the junk out of the backlog. And 5. Improve data transparency, using predictive analytics and mapping tools to help developers pick sites where the grid actually has the physical room to accept their power. We've covered a ton of ground today, peeling back the layers of this completely invisible energy network to reveal why simply building generation is really only half the battle. So I'm going to leave you with this final provocative thought to reflect on. Can our physical infrastructure ultimately match the blistering pace of our clean energy innovation? Thank you so much for joining me for this explainer. Keep asking questions, and I definitely encourage you to keep digging deeper into the fascinating physical realities that are powering our future.